Alright, welcome back to another IB Maths Calculus video. Today's video is going to be a follow-up on the previous one, so I highly recommend that, well, if you don't know things before the chain rule, like differentiating from first principles or limits, then I recommend that you watch those videos on our channel. Anyway, today's video is going to be about the chain rule, explaining how it works, and going through some examples. So without further ado, I want to write out the general way we denote chain rule. So dy dx, I cannot write. Dy dx was how we show the differential of a function. In general, this can come in many forms, so remember this is the one we're getting used to. So dy dx, yeah, there are a lot of different types of functions out there, and you may come across something like this. (2x plus 6 to the power of 7. You might be thinking, oh yeah, just power rule. Remember, we learned the power rule last time, where we can put in or multiply by the indice and then take away 1. So that becomes our our differential. Well, this is actually not the case. It's unfortunately not that easy. Maths is often not easy, and the reason for this, you might be wondering, well, why? The chain rule, we use the chain rule to differentiate functions when we have, let's say, sort of one function inside the other, or two different functions, and we have to find the differentials of them separately. There are lots of shorthand methods of doing this, which honestly I'm used to, and you quickly get used to just doing it from your head and just kind of packing, like putting the differentials and the numbers here and there, and you gradually get very used to it. But because this is an introduction to this, I should probably write introduction up here, huh? But because this is an introduction and an explanation video to this, I'm going to remain consistent and easy through the process, because this isn't a video testing you on how much you already know. This is a video on helping you get to know this. So we can't just do this for a differential to this function, right? So what's going on there? I said that there are two functions in this. Yes, so if we take 2x plus 6 to the power of 7, this would be quite literal hell to expand out into a polynomial and then, multiply it all together and differentiate by power rule. That is probably the worst way. That is the worst way you could do this. So what we do is we go like, okay, well, this is the inner function, this 2x plus 6. This 2x plus 6 is what we call our inner function. An inner function is kind of hard to define, but if I were to put it into the best words, then I would just define it the way it's called. So kind of the inside thing, the thing that you start with, almost the thing that you start looking at first. So something that's being done to something. Wait, give me a second. Wait. Something that has something done to it first is the innermost function. That might be a little bit convoluted, but just stay with me here. So this 2x plus 6 is what we define as the inner function. In this case, let's say this is y. I'll write this out here so it's a little bit neater. fx, or y, however you please, is 2x plus 6 to 7. And we want to find the differential of this. So we just said that this 2x plus 6 here, this is our inner function. Let's denote that as u. u is 2x plus 6. And an inner function implies the existence of an outer function as well. What might our outer function be? I'll just give you a second to think. Pause the video. So our outer function is this. It's going to involve this power, and we're going to denote it in terms of v. V is u to the power of 7. Makes sense, right? U is 2x plus 6. Put brackets around here for consistency's sake. And u to the power of 7 is v. And if we want to find the differential of this, then we have to acknowledge the existence that there are variables in both cases. And because there are variables, we have to differentiate them, I'm going to say separately, and then combine them together. It is an iffy explanation at best, the chain rule, and the way it's taught in textbooks in school, but I will try my best. So if we were to differentiate, kind of think of it in this way. If I want to find the differential of this whole function fx, I want to kind of differentiate these two separately and then sort of combine them together. That's what the chain rule is, and I don't think I can break it down further than this. If I were to show you a big moving graph and a lot of numbers and animations, then you just kind of see how this all works out, but that is incredibly difficult to put into words, so I'm afraid you'll just have to watch by example and by me writing it out. So we're differentiating these two inner and this inner and this outer function separately, and then we're kind of them together to combine it into one, which is going to be the differential of fx. So let's get started. So du dx is going to be 2. Why? 2x, remember, that's 2x to the 1. Bring the power down, multiply it, and then minus 1. Anything to the power of 0 is just 1. X to the power of 0 is 1. And 2 times 1 is just going to remain 2. And whenever we differentiate constants, they disappear from our equation. So du dx is going to be 2. So that means du, differentiated in terms of dx, is going to be 2. Now what about v? dv dx is going to be 7 times u to the 6. And this looks similar to what we just did here, right? But there's an extra catch. And yes, if you spotted this correctly, this is the power rule, essentially. You can replace this with whatever variable you like to help, x or y or whatever. But differentiating u to the 7 in terms of x is going to give us 7 times u to the 6. Because power rule, multiply by the power becomes the coefficient, and minus 1 up here. So that's that. And we still see this u remain in here, correct? And remember how I said we're going to combine these two differentials and kind of merge them into one? So that's pretty much just quite literally du dx times dv dx. And that's going to give us our differential of fx in terms of dx. Now, I don't want to sound condescending and be like, it's that simple, but essentially it is that simple. So let's do that immediately, shall we? 2, as du dx is 2, times 7 u to the 6. It's going to be 14 times u to the 6. Remember what u was. We defined u over here as 2x plus 6. So this just becomes 14 times 2x plus 6 to the 6th power. And that is our differential for fx. That is the chain rule. To recap, the chain rule is finding kind of an inner and an outer function, defining them separately. Most often, you define the second type in terms of the first one, so in terms of u, differentiate them separately, and then multiply them together to combine them to get your original intended function's differential that you wanted to find, which in our case was this fx right here. Now, that's it for the explanation bits. Now, I will run through some examples. So, let me just think of some. Let's do something similar to this. So, 8x squared plus 5 to the fourth. I'll pause the video, and I want you to try this on your own as well. 8x squared plus 5 brackets to the power of 4. We're going to find the first differential. Okay. So how do we do that? Well, remember, we need to define an inner function and an outer function. So in this case, our inner function remains this. 8x squared plus 5. Let's write that down, shall we? U is 8x squared plus 5, and v, we should write down in terms of u. U to the 4. Sorry, my 4s are a little weird. It's my pretty shorthand form. I can make them nicer for you guys if you want. But yeah, I'm just saying these weird little h's are my 4s, so please don't get weirded out by that. Anyway, now we differentiate them separately. Du dx is 16x. Remember, constant disappears, and power rule for this. dv dx is going to be 4u to the 3, according to the power rule. And now we combine them by multiplication. So du dx is 16x times 4u to the 3. That's going to equal 16x times 4, 8x squared plus 5 to the 3, and 16 times 4 at the top of my head is 64. 64x times 8x squared plus 5 to the 3 is dy dx. Boom. First example done. Now, I do not want to confuse you, but this whole thing of kind of combining them, it's really simplified by the multiplication, and it's conceptually it's not that easy. If you want to read into this more, you're more than welcome to, but the chain rule is an interesting one, because this expression here, the du dx times dv dx, well, excuse me, I use dots for multiplication, times, here as well, is kind of our way of showing how these two differentials interact and then kind of coalesce into our original one. I won't be showing the proof for that here today because it is pretty complicated and it is not on your syllabus, and I don't believe that's very important for you right now. You're, again, more than welcome to look that up on your own. But yes, I just wanted to put that out there. So let's think up something different this time. A little bit harder one. 4x to the 5 plus 3x squared to the 5. Why not? Give you pause the video and I'll take however much time you need. Okay, so again, I'll be moving quicker now. 4x to the 5 plus 3x squared is u, and v is u to the 5. So differential of this, just power rule again, 20x to the 4 plus 6x, and dv dx is just 5u to the 4. Now we we kind of combine them via multiplication. Excuse my dots, that's how I denote multiplication, and it's a habit if you're not familiar with it. It's going to be this. These can get much longer and much uglier as they increase in difficulty. So we have the 5 in front of there, we can just do this. Plus 30x all times the original u, which is 4x to the 5 plus 3x squared to the 4. That is our differential for this function. Now, third one. Let me take a minute to think of a little bit harder one. Okay. I've got a harder one. Let's say yeah, that sounds pretty annoying. All right. So 2 over x to the power of a half. I want you to pause the video and attempt this on your own. Okay. Again, we follow the same procedure. U is 2 over x, and v is u to the power of a half. So, du dx, what's it gonna be? Well, if you're good with indices, and if you're good with indices, then you're gonna recognize that, well, 2 over x can be expressed, I cannot speak, 2 over x can be expressed as 2 times x to the negative 1. And then you're like, aha, yes, power rule. That definitely applies here. Do apply the power rule. That's actually how you do these sorts of things. So that's going to be, well, minus 1 times 2. Oh, this is actually incorrect. Just arrow then. Minus 1 times 2 is minus 2. And minus 1 is minus 2. So minus 2x to the minus 2 is going to be minus 2 over x squared. That's your du dx. And b, dv dx. What's it going to be? Well, power is a half. What's a half minus 1? Well, negative a half, no? Kind of the doy moment. So power rule, again, nothing changes here. 1 over 2 times u to the power of negative a half. And if you're a smart cookie, big brain guy, you notice that something to the power of half is essentially just the square root of it. But when we're differentiating in terms of roots, then it is common practice to turn them into indices because of this reason, because power rule is just such an easy thing to use. So this is going to be dv dx. 1 over 2 times u to the power of negative 1 over 2. And if you want this in terms of fractional form, then it's going to look something like, yeah, this. 1 over root u. That's what it will look like. Now, how do we recombine all of this again? Same exact step. Du dx times dv dx. So it's going to be minus 2 over x squared times, 1 over 2 root u, which will just turn into, we have to substitute in our u term, minus 2x squared, 1 over 2 root, what was our u? 2 over x if you really want to put this into one thing, then if you multiply these, minus 2 over 2x squared root 2 over x. That is your differential for this. Now, I will do one last one for yes, because I feel like it's appropriate. This last one's going to be the hardest one, so brace yourselves. I think of something like this again. Something really ugly. Okay, yeah. Yeah, this is disgusting enough. Let's use it. Okay. 3 over x cubed minus 1 over x squared, all to the power of 3 over 2. Give you a minute. Pause the video. Take however much time you need. Okay, you good? Alright, let's go. Again, inner function u. 3 over x cubed minus 1 over x squared. Differentiate it. How? Remember this whole indice and fraction thing we just talked about? Minus 2 over x squared can be expressed as minus 2 times x to the negative 2. So, following that same rule of thumb, 3 over x cubed can just be expressed as 3 times x to the negative 3. And if you differentiate that using power rule, we get negative 9 x to the negative 4. And then the second term here, remember this is a minus sign, and this is technically x to the negative 2. So minus 2 times minus 1 is just going to be 2. So plus 2 x to the minus 3. Because remember, to the negative 2 minus 1 is minus 3. That's going to be your du dx. Now for our v term, surprisingly slightly easier, v is u to the 3 over 2. Same exact thing. What's 3 over 2 minus 1? Well, that's just 3 over 2 minus 2 over 2. It's just 1 over 2. So this becomes, so dv dx is 3 over 2 times u to the 1 over 2. And this is pretty ugly. This is pretty disgusting even for me. And I've done my fair share of gross differentiation and calculus and integration. You don't know what that is yet, but you will find out in time. Or combine them. du dx times dv dx. Gonna be a whole shebang. So let's put this on nicely. So minus 9 over x to the 4 plus 2 over x cubed. Brackets this 3 over 2. I don't have enough space, do I? I don't have enough space. Okay. How do I'm just gonna cross this out. Okay. Du, I'm gonna write it down here. du over dx times dv over dx is gonna be minus 9 x to the 4. Oh my god, I suck. Minus 9 times 3. Minus 9 x to the 4 plus 2 over x cubed. Brackets, multiply dv dx. 3u 1 over 2 over 2. And u is pretty big and annoying, so minus 9 x to the 4 plus 2 over x cubed. There's 3. Remember, substitute in our original u value to the half or root, however you please. And I'm not gonna bother combining this any further. I'm not gonna bother expanding this any further. If you get an exam question like that, guaranteed that they will accept this form. This is dy dx. And that is the last problem I will do. I can get more annoying and more difficult, but that's just me being it's just me insert some clever idiom in. Okay, that was chain rule. I hope that helped. I hope it helped. We went through 4 different examples, varying in difficulty. I hope you understand the method a little bit better. Thank you for watching. Again, thank you for sticking with our videos. Today was actually unscripted, so pretty proud of myself, tooting my own horn. Yeah. See you in the next video, guys. The next video will be about differentiating trig functions, ln functions, and exponentials. So that will be my peer doing that. Anyways, I will see you later. Catch you later. Bye-bye.